Welcome to PhysiCast, physics podcast for 14 to 19 year olds. All of our podcasts are available on www.physicasts.co.uk. To get the most out of this podcast, if you're watching the video and you see the pause icon, or if you're listening to audio and you hear me say pause, have a go at the activity, and then when you've had a really good think about it, unpause it to find out what the answer is. GCSE of Science, Episode 1, Making Things Hot. Today we're going to recap states of matter and 4 different ways in which energy can be transferred as heat. First of all, I'm going to start by telling you what heat is. Heat is simply the amount of energy that an object has which causes its particles to vibrate. Temperature is a measure of how much particles in an object are vibrating. Hot objects give out heat, colder objects will take in heat. We're going to start by looking at the 3 states of matter that you will need to know and be able to describe. So I'd like you to draw 3 boxes on a piece of paper. Write solid, liquid and gas underneath them. In those boxes, I would like you to draw a few particles and construct a particle diagram for each of solid, liquid and gas. Draw about 9 particles in each box. I'd like you to take care showing how the particles are arranged, and I would like you to describe what the particles are doing in each picture. So go ahead and pause the podcast, draw that out, and then play the podcast again when you're ready to check your answer. Okay, if you're watching the video, you'll be able to see the pictures on the screen. Otherwise, if you're listening to the audio, I'll describe the particles for you now. In a solid, I've drawn my 9 particles in a grid-like arrangement. So I've got them in even, regular rows and columns. They follow the same pattern throughout the structure. They're not random, they are organised in neat lines. Each particle is actually held by a little bond between the two. So these bonds are like glue that stick the atoms of particles together. All the particles are the same size. What are they doing? Well, they're not moving around each other. They're not able to because they're bonded together, they're stuck in place. So what they're actually doing is they're just vibrating on the spot. So if you imagine a bunch of people sat in seats, perhaps at a football match, in their rows and their columns, and they're not really able to go around each other because they've all got their own seats, but what they are, they're very excited by the match, so they're sort of moving about in their seats, or perhaps they're stood up. If you give your solid more energy and excite these particles more, then they'll start to, like fans at a football match, they'll start to jump about more. They won't be able to move around each other, but they'll be able to vibrate more on the spot. Eventually, if you give these particles enough energy, they'll actually be able to move around each other. This is when you get melting and your conversion into a liquid. So in my liquid diagram, I've got the same number of particles. They're exactly the same size, because when you heat something, the actual particles never change size. They just move apart. These particles are still touching. They still have roughly the same volume that they occupy, but they're able to move around each other. All that order, those columns and those rows, they're gone. They're randomly placed. Those bonds now between the atoms are broken and they're able to move around each other. They're drawn at the bottom of the square because they take the shape of the container. So if you melt an ice cube in, say, a mug, then that water will spread out and fill the bottom of the container. It won't be able to go anywhere else apart from the bottom. So if you want to get those water molecules out of your mug, then you need to actually heat them up even more. So when you give liquid particles even more energy, then they have enough energy to be able to break free of that water, and they leave the surface of the water. This is called evaporation, and that will turn into a gas. So our water would turn into steam. So my particle diagram, again, the particles are exactly the same size, but now they're really far apart. What I can't really do justice to on this diagram is just how far apart those particles are compared to the solid and liquid. They're really, really far apart. They're also moving around really, really quickly. They're bouncing off each other, they're bouncing off the walls of the room, they are colliding really violently. In the room you're in right now, at standard room temperature, the average speed of a molecule of gas is over 500 meters per second. That's really, really quick. However, these particles are actually all constantly bumping into each other, so you don't ever experience that speed, which is really lucky, or else you'd probably get knocked off your feet. Right, now that we've got the three states of matter sorted, we can look at the 4 ways that you can transfer thermal energy from A to B. The first one is called thermal conduction. Thermal conduction is the transfer of thermal energy by the collision of particles. In the video, I've shown a picture of 4 particles drawn side by side in a row. So you can imagine that this is a metal rod and we've got particles along the rod. What are they doing in the solid? Well, as I said, they're vibrating on the spot. If they've got more thermal energy, if they're hotter, then they'll be vibrating more. So I'm going to heat my rod from the left hand side with a heat source, like a flame. This causes the left hand particle to start to vibrate more. So it vibrates faster and it also takes up more space. It vibrates further from its rest position. If you heat up this particle enough, it will then collide with the particle next to it. It's like if you were sat in your seat and you were shaking side to side, you would bump into the person next to you. So what would happen when you bumped into them? Well, they'd get knocked over, wouldn't they? They would get bumped themselves. So that energy that of you hitting into them would then be passed on to them. So they would gain that energy from you, and you would lose that energy. It's like on a snooker or a pool table. When the white ball hits the black ball, the white ball will slow down. It will give its kinetic energy, that's the energy of movement, to the black ball. So the black ball will move faster, the white ball will slow down. So back to our metal rod, what's this got to do with it? Well, the particles, when they collide, that's how they pass on their energy. So if I'm heating from one side, those particles will in turn hit each other. So the particle that will get the heat energy last will be the particle furthest away from the heat source, which will be on the right in our diagram on the video. Eventually, when you've heated them long enough, then all the particles will have all had a chance to collide with each other, and they will have spread out the energy throughout the entire metal rod. And then when you've got that point, the whole thing will be at the same uniform temperature at all points along the rod, if you take away the heat source. So what sort of things can we have conduction happening in? Well, I said that conduction required the collision of particles. So our particles have got to be close together. Have a look at your 3 particle diagrams that you drew. Which one has the particles closest together, most easily able to bump into each other? It's the solid, isn't it? So conduction happens very, very well in solids. Conduction does not happen so well in liquids, and it happens very, very poorly in gases. You do sometimes get a little bit, but it doesn't happen very well. Within solids, you have different types of conductors. So something that conducts heat energy very well is called a thermal conductor. Something that conducts heat energy very poorly is called a thermal insulator. I'd like to pause the podcast at this stage and write down some names of solids that you know are good thermal conductors and good thermal insulators. Okay, now that you've written those down, I'm going to take you through what sort of things are good conductors and good insulators. Good conductors mainly include metals. Metals are very good conductors of electricity. You know that copper wires are used in electricity supplies, and because they have 3 electrons, so their atomic structure, they're able to lose some of the electrons from their atomic structure, and they're able to go anywhere they want in the object in the metal object. So they're not fixed on the atom. They're free to roam around from atom to atom. This is how electricity is conducted. This is also how heat is conducted in a metal. So the free electrons gain kinetic energy. This is our energy of movement, which is also our measure of temperature. So the faster things move, the hotter they are. So those electrons are able to move from A to B by skipping out all the atoms in between. They can go where they want, they can travel that thermal energy, they can conduct it really quickly, much quicker than having to bump each particle in turn to get from one end to the other. Things that are good thermal insulators are things like plastics, glass, any other non-metal really that's a solid. You can make solids better insulators by adding trapped air into them. Things like double glazing, which has air in between, is a good insulator. Bubble wrap, which has trapped air, is a good insulator. And of course, any liquid or gas are good insulators as well. A second thermal transfer is convection. Convection is the transfer of thermal energy by the movement of particles in a fluid. So fluids are anything where particles are able to move around. Have a look at your particle diagram. Which one has particles that are able to move around? There's two of them. It's liquids and it's gases. So a fluid is a liquid or a gas. So when you heat up a fluid, such as a liquid or a gas, then you give the particles more energy. When they have more energy, they move further apart, they spread out. Things that are less dense, like a helium balloon, where do they go? They rise. Think of a hot air balloon. If you heat up the air in the hot air balloon, those particles spread out, become less dense, and of course the balloon rises in the air. How do you make a balloon fall back down to earth? You switch the flame off. How does that help? The air inside the balloon cools down, contracts, particles become more dense, and so the balloon sinks in the atmosphere. So when you heat up a fluid, hotter particles rise and replace colder particles at the top of the fluid, and then cooler particles sink and replace warmer particles lower down. When you have fluids that are rising and sinking at the same time, this is called a convection current. Convection currents are happening everywhere on Earth right now. Convection currents are happening in the mantle of our Earth right now. So hot, molten, almost molten rock is rising when it's heated, and then as it cools, it then sinks back down. This is actually what's causing our tectonic plates to spread apart. Our third thermal transfer is called infrared radiation. Infrared is just one example of the electromagnetic spectrum, which is a big family of types of energy which all travel at the speed of light, and of course light is one part of that electromagnetic spectrum. But the part that we feel as heat is called infrared. It has a wavelength that is very similar to colour, but the wavelength is just slightly longer than red, so that's why it's called infrared. Now anything that's hot gives off infrared radiation, so you are giving off infrared radiation because you have thermal energy inside you. If you take a cup of coffee that is going to be hotter than your body, then that is going to give off thermal energy at a quicker rate, so it's going to give out more infrared radiation. Police use infrared cameras to detect heat at night. So anything that's giving out heat, bodies are very good at giving out heat at night, because they will show up on the thermal camera very easily, and you'll be able to see the people that they're chasing. Now infrared, unlike conduction and convection, can actually occur without particles. So infrared radiation is just simply waves of energy. There's no particles involved in the transfer of this energy. And because of this, infrared radiation can happen in space. Space, of course, is a vacuum with no or very little particles. It's a good job that infrared radiation can travel without particles, because otherwise no heat would be able to get from the sun to planet Earth, and of course we wouldn't be able to exist without the heat from the sun. Our final method of thermal transfer is evaporation. Evaporation is the loss of heat from a liquid when the most energetic particles, the ones which are moving very quickly, actually leave the surface. So if you imagine a beaker of water, and in there you have got particles. And those particles are moving around each other, aren't they? Well, they're not all moving around at the same speed. Some of them are moving a lot quicker than others. Some are just luckier and they have more energy. And eventually, over time, they'll lose that energy and then they'll gain a bit more energy. But on average, the temperature of the liquid will stay the same. Well, if these particles get really lucky, they will gain enough energy to be able to, by chance, leave the water. Evaporation happens very slowly if it's a cool day. So if you take a puddle of water, if you watch it, you don't see it boiling, of course. You don't see bubbles forming. You're not going to see steam rising off it. But if you come back later in the day, particularly if it's a warm day, then you'll see that the puddle has gone. So all the different particles have different amounts of kinetic energy, and it's the particles with the most kinetic energy that leave the liquid. If the particles with lots of kinetic energy leave the liquid, then on average the liquid will have lost kinetic energy. And we said at the start that kinetic energy was a measure of temperature, it's a measure of how hot something is. So by taking that kinetic energy away with them, they're actually cooling the liquid. An example of evaporation is, of course, sweating. So when your body is hot and you need to lose heat, you will sweat. So your sweat glands release sweat onto your skin, and sweat is just simply a liquid that's there to be evaporated. So your sweat will evaporate over time, so the particles with the most kinetic energy will take away that energy from your body. And over time, that sweat will cool and your body will be cooled because the energy is being taken away and into the air. If you want to increase the rate of evaporation, you can do three things. So you can increase the surface area of your liquid. So water that's spread out into a puddle will evaporate a lot quicker than water that is kept in a test tube. You could increase the temperature of your liquid. So a puddle will evaporate a lot faster on a warm day than it will on a cold day. The final thing you can do is you can create a draft across the liquid. So if you're drying your clothes on a windy day, you will be able to dry them a lot quicker. This is because when liquid molecules escape the surface of a liquid, they hang around above the liquid as water vapour. Well, when they've left the liquid, there's a chance that they might come back and condense into the liquid. So what we really want to do is not just evaporate the water, but actually then take that water vapour and move it away from the puddle, or move it away from our wet clothes. So wind, or draft of air, is a really good way of doing this. If you've got a hot cup of coffee, you can blow across the surface of the coffee, so that any hot coffee vapour that is rising above the coffee then gets taken away, and then some more hot coffee vapour is able to rise into that place. Condensation is the opposite of evaporation. So condensation is when gas turns into a liquid. So you get this when you have a shower. So you create hot water vapour from the shower that hangs around in the atmosphere. It then hits a cool surface such as your window or a mirror. When it does that, it loses its energy and it turns into a liquid, and you get the water droplets forming on your mirror. Right, so we've looked at 4 different types of thermal transfer. If you've written them down, which I hope you have, I'd just like you to not look at that sheet of paper and see if you can remember what the names of the 4 types of heat energy transfers are. And I'd also like you to try and give an example of each type of heat transfer. So what sort of materials would they happen well in, and when would they happen? Right, so our 4 types of thermal transfer are conduction, which happens well in solids and is the collision between particles that are moving. Convection, which is the movement of particles in a fluid. Radiation, which is the transfer of energy as a wave and does not require particles. And evaporation, which is when particles with higher kinetic energy leave a liquid, taking away that energy with them, and so the liquid is able to cool. Well, I hope you enjoyed that first podcast of the Additional Science series. You can take this further now by going on to the links on the last part of the video, or having a look at the links on our website page for this episode. I'd advise you to have a look at a second source of information. So I've given you a link to BBC Bitesize, which is related to energy transfers. A good way of revising this will be to read through the content on that website, add to your notes from this podcast, and then finally attempt the quiz. And then any questions which you don't get right, you should make a note of them, and then you can take them in and let your teacher know, and then they'll be able to go through those questions with you. Our next episode is called Designing an Eco House. So we're going to take the energy transfers that we've looked at today and put those into practice. How can we use them to save money on our heating bills? Thank you for listening, and I hope to see you again for the next episode. This podcast was an episode of Physicasts, physics podcasts for 14 to 19 year olds. Physicasts is written and produced by Tino Race. You can find out more about Physicasts on our website, www.physicasts.co.uk.